Hi, welcome back. This is Rakesh Naik. Today we are going to start about trees. There is one more data structure. Till now we have seen data structure which is linear by nature. And today we are going to see one more data structure which is non-linear by nature. Today we are going to learn about trees. So before we start, a small information I'd like to share. In this channel we produce every video in two different languages, Hindi as well as in English. If you want to watch this video in Hindi, kindly follow the link given in the description. And if you have not yet subscribed, please subscribe and press the bell icon so that you will get regular updates from this channel. So, let us start. Till now we have seen data structure which are linear by nature. And today we are going to learn a non-linear data structure which is tree. In linear data structure we have learned about stack and queues. We need arrays and linked lists to represent these linear data structure. In a linear data structure, if I know the first data, then I can traverse all the data in a linear manner. But it is not like that in every day-to-day life situation. So when the data are in a hierarchical relationship between themselves, then we need a special kind of data structure called a tree. So in this video, we are going to say about different terminologies that we are going to use and how generally we represent a tree using the basic data structure like array and linked list. So let us go to the basic definition. So a tree is defined as an acyclic and connected graph, and it doesn't contain any loop or any cycle. So there is no more than one edge between every pair of nodes. So a tree I can define recursively as a set of nodes. Out of these nodes, one node will be treated as a root node, and the rest of the node I can partition them into non-empty subsets which are like left subtree and the right subtrees. So this I can say is a tree. Your family relationship, like your grandfather, the grandfather having children, now your father having children, and you may be getting married someday and you will be having children. Such kind of relationship I can represent with the help of a tree. So let us go to the basic definitions. Then what is a root node? The topmost node is known as root node. Now as I given you the example of your grandfather, so the grandfather can be the root node of a particular family tree. So here in this tree I can say node A as a root node. One more term is parent node. Parent of a node is immediate predecessor of the node, and similarly child node. Child node is an intermediate successor of a node, is known as a child node. Like here, if this is a tree given to me, in this tree, node B and C are the children of A, and node B is a parent of node D and node E. So B is a predecessor of D and E, and B is a successor of A. There are two more definitions, descendant and ancestors. So a node that can be reached by repeatedly proceeding from a root to child is called a descendant node. Similarly, the opposite is if I can proceed from child to the parent node and ultimately reach the root node, then I'll say all of them are ancestors. So in this tree, you can see the descendant of node A is B and D. Similarly, B and E. Similarly, here C and F and C and G. All of them are the descendant of A. But for node D, the ancestors are B and A. You can see B and D are descendant of A. Similarly, B and E are descendant of A. And A and B are ancestor of D as well as for node E. There are few more terms we use. One term is sibling. The children of a given node is known as children. A node with no children, it is also known as external node. And internal node are those nodes which is not a root node or which is not a leaf node. So it means a node with at least one child I will say as an internal node. For example, here you can see B and C are siblings. They are child of A. Similarly, D and E are siblings. Here B and C are the internal node. They are having at least one child. And D, E, F, G, they don't have any more child here. So that's why we'll say them as a leaf node. Now degree of a node and degree of a tree. So number of subtrees of a node, I'll say degree of a node. And the maximum degree of a node in a given tree, I'll say degree of a tree. For example, here you can see the degree of A is 3 because there are 3 subtrees that is coming out of A. Degree of B is 2 because there are 2 subtrees coming out of B. And degree of H is 0. There is no subtree connected to H. Similarly, degree of tree is 3. Why? Because the maximum degree of any node is 3. Few more terms that we use is edge and path. Connection between two nodes, I'll say an edge, and a sequence of nodes connecting to a node with its descendant is called a path. Here you can see there is a connection between node A and B. This I'll say an edge. But a path is like from A, if I start, I can go to B, then I can go to D. So from A to D there is a path. Similarly, A to B to E there is a path. So these are known as paths. These two definitions are very, very important. Kindly listen to it very carefully. First definition is height. The height of a node is the number of edges from the node to the farthest leaf. And the height of the tree is the height of the root. We'll discuss about it. And the depth is, it is the number of edges of a node to the root node. From a node to the root node, if I'll go upward direction, I'll say it is a depth. And from downward direction, if I'll go, I'll say height. For example, you see here, in this particular diagram, the height of H is 0 because H is the leaf node. I cannot go to the farthest leaf anymore. The height of A is 2. From A, the farthest leaf is of distance 2 edges. So the height of A is 2. The height of C is 1. You can see here, C is the node here. The farthest leaf node from C is G. And it is at a distance of 1 edge. So I can say the height of C is 1. Similarly, the definition of depth. Depth of H is 1. In a reverse direction I have to take. The given node, how many edges far away from the root? A is the root and H is 1 edge away. So that's why the depth of H is 1. The depth of E is 2. So E is at a 2 edge distance from the root node. Similarly, depth of C is 1. C is at 1 edge away from the root node. So these are the basic terminology that we are having. Now let us see what are the basic type of trees that we have. First is a general tree. It is a connected acyclic graph. That's why how we are going to represent it, it doesn't matter. So it is also a tree. So it is a connected graph and it doesn't contain any cycle. So it is a tree. The next type of tree is a forest. A forest is a set of disjoint trees where n is greater than or equal to 0. These collection of trees are called as forest. So there are more than one tree available here. Next definition is rooted tree. It is a connected graph when one node is called root and whose incoming degree is 0. So for this particular node, there is no incoming edge to this particular. So this is called a root, and this kind of tree I'll call as a rooted tree. The next definition is regular tree. Except the leaf node, all the nodes having same out degree. Look at this definition, where the first node having degree 3, the second node B is having degree 3, the third node C is having degree 3. If at all there is a out degree, it's supposed to be having same. So such kind of tree I'll say a regular tree. And to the extension of this I can say regular M-array tree. If the out degree of every node is less than or equal to M, then I'll say it is a M-array tree. The next definition is a binary tree. In a binary tree, each node has either 0 or 1 or at most 2 children, then I'll say it is a binary tree. So you can say binary tree is an example or a special case of M-array tree. You can see here, this is an example of a binary tree. If a node is there, then that node will be having either 2 or 1 or 0 children. So such kind of a tree I'll say as a binary tree. Take another kind of tree, that is complete binary tree. Each leaf node in a tree is at either at level D or at level D minus 1. If the right descendant of a node is at depth D, then the left descendant also is at depth D. For example, here you can see the level of all the leaf nodes are same. So if the left subtree is at depth D, the right subtree is also at depth D. It is possible if the left subtree is at level D, then the right subtree can be having one less, that is D minus 1. In another way, if I want to say, if the right subtree is at level D, then the left subtree has to be at level D. This is one more example you can see. The left subtree is at level D, then the right subtree is one less, that is D minus 1. So this kind of binary tree I'll say as a complete binary tree. The maximum possible number of nodes in all levels. It is also known as perfect binary tree. So you can see here, so each leaf is at same level. It means the maximum number of possible nodes in all level. So at this level there are 2 possible nodes. At this level there are 4 possible nodes. So in the next level there will be 8 possible nodes. So in that way I can say this is a perfect binary tree. This formula is very, very important. Generally in exams they ask the total number of nodes in a full binary tree at height h is 2 to the power h plus 1 minus 1, considering root as level 0. So how many nodes are there? You can see there are 7 nodes and the height of this tree is 2. So 2 to the power 2 plus 1, that is 2 to the power 3, 8 minus 1. So total number of nodes in this particular full binary tree is 7 according to this particular formula. So one more type of tree is strict binary tree. So if every non-leaf node in a binary tree consists of non-empty left and the right subtree, then I'll say it is a strict binary tree. In this example you can see every non-leaf node is consist of a left subtree and a right subtree. So this kind of a tree I'll say it's strictly binary tree. One more kind of tree is called a left skewed binary tree. So it means if the right subtrees are totally missing, then I'll say it is a left skewed tree. Similarly, the right skewed tree are there where the left subtrees are totally missing. There are few properties of tree. We'll see one by one. The number of vertices is 1 more than the number of edges in a tree. A tree with 2 or more vertices has at least 2 leaf nodes. And the third property is there exists unique path between every 2 vertices. Based on these properties, in competitive exams they ask questions. And let us see few properties of binary tree. The maximum number of nodes of level L in a binary tree is 2 to the power L plus 1 minus 1, where L is greater than equal to 0. One more property is there. The maximum number of nodes in depth D in a binary tree is 2 to the power D minus 1. These two formula are also very, very important. So basic operations that we generally do in a binary tree is we create a tree, we traverse a tree, we insert element into the tree and we delete. So there are 2 ways this hierarchical a relationship between nodes represented with the help of a tree. So we can use an array or we can use a linked list. These linear data structure to represent this non-linear or hierarchical relationship between the nodes. So let us see how I can represent using an array. These are few things that we need to remember. If I want to represent using array, if tree is an array given, then 0th index I'll write the root of the tree. If there is a node at ith index of the array called tree, then the left child will be at 2i plus 1. The right child will be stored at 2i plus 2. If I know the child index, then I can know the parent index by I minus 1 by 2's lower bound. We'll see one by one. Let us say this is a tree given to me and I want to represent it with the help of an array. So what I'll define a array called tree, and at 0th index I'll write the data A. First index I'll write B. Second index I'll write C. Then D, E. Here there is no children, so I'll leave two places. Then for D, the left child is F and the right child is G. So at 7th and 8th location, F and G is written, and the 9th index H is written, and rest there is no children. So I'll leave it empty. Now you can see at 0th index is the root. Yes, it is the root at 0th index. So the first index data B is there. Its left child will be there at 2 into 1 plus 1. That is at index 3. Let us verify. So the left child is at 3rd index and the right child is at 4th index. That is 2 into 1 plus 1 is the index of data B. Let us say at the 7th index data F is there. I want to find its parent. So what I need to do? 7 minus 1 by 2. 7 minus 1 is 6. 6 by 2 is 3. So at 3rd location, D is the parent of F. You can see, you can verify it. Now, with the help of linked list, I have to create a node like this, having 3 parts. The left part will contain the address of the left child. The middle part will contain the data, and the right side will contain the address of the right child. And if I want to represent it, I'll represent it in this way. If I'm starting, let us say node A is the root node, which is defined at location 2098. On the left hand side, memory address 2094 is defined. At 2094, again a node I'll find with data SB, and 1094 is the memory address given on the left hand. So the left tree is located at 1094 location, and there is no address kept here. So this is the leaf node. Similarly, at 1024 data E is defined, so I'll write the data E as 1024. Similarly, towards A's right, memory address 1040 is written, so at 1040 I'll find the data C, and onto its left I'll find 1084 memory address. If I'll come to 1084 memory address, I'll find a data called F. So in whichever node, if I find the left and the right addresses to be null, then I'll say this is a leaf node. So I hope you understood what is a tree, what are the terminology that we are going to use, what are the different type of trees that we are having, and how generally we represent it using array and using linked list. In our next video, we are going to talk about tree traversal. So see you then. Take care. Bye.